Okay. Our next problem is that we are very familiar with the differentiability of real-valued functions. For real-valued functions, we have the mean-value theorem and many other results. So now we have introduced the differentiability of vector-valued functions. So a natural question is there are relations. The relations between vector-valued differentiability of vector-valued function and real-valued function. So this proposition answers this question. F is differentiable at A if and only if the components for all I, the component function which are real-valued functions, okay, are differentiable at A. Okay, so the proof of this proposition is very easy. Proof. In our study of Euclidean space, when we study the convergence of sequence and the component-wise convergence, the relation between convergence and the component-wise for sequence in Rm, we have an inequality. Now we apply the inequality here. We have fi a plus h minus fi a minus ai h will not greater than a plus h minus fa minus ah because the left hand side, the term inside the norm on the left hand side is the ith component of that on the right hand side. So we have this inequality, and then we also have okay, this is an obvious inequality. Following this inequality, we can prove our if and only if. First, we will prove the only if part. Only if part. If f is differentiable, we will prove that for every I, fi is also differentiable. And we have the following inequality: fi a plus h minus fi a minus ai h divided by the norm of h. By the first inequality here, we have this will not greater than fa plus h minus fa minus ah divided by the norm of h. The right hand side goes to 0 as h goes to 0. Okay, therefore the left hand side also goes to 0. The left hand side goes to 0 means that fi is differentiable at A. Okay, so this proves the only if part. To the if part, we can use the second inequality. Okay, so I will omit this here. Now we study the computational property of differentiability and derivative. So proposition. Suppose f and g defined in a neighborhood of A, vector valued, are differentiable at A. Then the first result, for lambda mu real numbers, lambda f plus mu g, this is also a map from the neighborhood to Rm. The value of this map at the point x is lambda fx plus mu gx. Okay, this is the definition of lambda f plus mu g. This map is also differentiable at the point A. Okay, so the linear combination of differentiable maps is differentiable. Moreover, we know that the derivative of lambda f plus mu g at this point A is lambda f prime A plus mu g derivative of g at A. Okay, so what's this equality? This equality is an equality of matrix. Okay, the right hand side, lambda f plus mu g is a map from n-dimensional ball to m-dimensional space. So the derivative is an n by n matrix. Similarly, our f is from a ball in Rn to Rm. Therefore, the derivative of f at A is also n by n matrix. So also that of G. So this is an equality of n by n matrix. Okay. The second result, the inner product of f and g, which is a real valued function generated from the two vector valued function defined in the same neighborhood to R. The value of the inner product function at the point x is the inner product of fx and gx. Okay, so this function is also differentiable at A, and the derivative can also be given by the formula. This is the transport of fa g prime A plus the transport of g f prime A. Okay, this is the derivative of the inner product function. So this is a equality for vectors because f prime g is from n-dimensional ball to R. Therefore, the derivative is 1 by n matrix, which is a row vector. Similarly, the two terms in the right hand side, the first term in the right hand side, the transport of fa is 1 by m because fa in Rm. We use the transport notation because we write fa in column vector. So therefore the transport is a row vector, and the g prime A is n by n matrix. So the multiplication is 1 by n. This is also 1 by n. Similarly, the second term is also 1 by n. So this is an equality for 1 by n matrix, or you can say equality for row vectors. Okay. Now, the proof of the first conclusion is very easy, so I will not prove it here. I will prove the second result. This is the proof will demonstrate the basic idea useful in our other problem. So proof. since f and g are differentiable at A, we have two functions, eta and delta, defined on the R neighborhood of A, take a value in Rm such that the limit is 0. H goes to 0, eta h 0, h goes to 0, delta h 0. Okay, and also f a plus h is f a plus ah. A is the derivative of f at A plus eta h. And for g, ga plus h is ga plus the derivative plus delta h. This are consequence of the differentiability of f and g at A. Now we compute the inner product function at the point A plus h. Using the previous two equality, this is f a plus f prime a h plus eta h inner product with ga plus g prime a h plus delta h. And we expand this inner product, we get f a g a, these two terms. These two terms, and fa inner product with g prime a h, these two terms, and also f prime a h inner product with ga, this term. Okay, these three. The other terms we collect together to get to write capital theta h. Maybe I don't need to use capital, simply theta h. Okay, now we go forward. F a g a plus this inner product. The inner product of two we consider as column vector is the transport of the first multiplied the second. So this will be the transport of f a g prime a h. So what's this? F a we consider as a column vector. Its transport is a row vector. Then g prime a is a matrix m by n. This is 1 by m. And h is a column vector. So n-dimensional column vector. So this multiplication is 1 by n. It is a real number. It's a number 1 by 1. Okay. Similarly, for the second term here, we switch GA and we switch these two factors for inner product. So we can write as GA f prime a h. Then we use the previous trick to write as the transport of G. So we get plus the transport of G f prime a h and the theta h. Okay.